application in material science is challenging. I think all of us are confronted with this. It's often the case that there is a needle in a haystack problem. We need to find one optimum in a very large chemical space. It is a multi-scale problem. Everything is important, from atomic scale interaction to the processing and manufacturing of the actual devices at the nanometer or meter scale. And this is because there is an interplay between the property of a material, which is determined by its structure and microstructure, which in turn is determined by the way in which we process such a material. And I think we can see the digital materials revolution and the idea of having machine learning application to materials and molecules as an enabler of a paradigm shift where we surpass a number of bottlenecks. And this is because we have access to an efficient and agnostic exploration of chemical spaces. We have a fast and accurate approximation of complex calculations, such as the one relevant to quantum and molecular mechanics. And arguably, we have access to a tool which enables the unbiased systematic analysis and discovery of materials. And I'm very proud of this tool because I think we will see a number of these different applications across many different relevant domains. And once more, I think we are seeing this interest in the area being relevant across different players with different budgets and capacities. And this is really where cost action enters into play. We do know that there is a reward for materials acceleration, which according to Boston Consulting Group was evaluated in the order of 30 trillions. And this reward, of course, enhances a race to get and maximize the outcomes of this reward. And so what we are famous in Europe is not just bureaucracy, but also solidarity. And the idea of cost is really building upon this reflection. So cost receives funding from the European Commission and then delivers them to a number of networks, such as costs, under the idea of promoting and spreading excellence through capacity building and research coordination. So indeed we have these aspects of driving excellence and having that developed in an equal way as a level playing field, at least within Europe and actually beyond. We have an aspect of capacity building, which is really training the new generation of scientists, and as well as upskilling the let's say, less new generation of scientists that want to explore a given area. And last but not least, by coming together, we can identify and coordinate to understand which are the most relevant areas within a certain domain that we think are the most relevant. And cost is really pan-European, so in purple here you see some of, let's say, the standard nations you would think as Europe, but Europe is larger, and in green it's actually all the European and extra-European countries that, in a sense, you can see also geographically lied at the periphery and could, in a sense, benefit largely from a cost action. I want to stress that there are also interactions, for example, with Middle East and North Africa for the same reasons. So you can have access to our document, our memorandum of understanding, which describes all the hows and whys in relation to DEMON objectives and the challenges that we want to tackle. And again, I think I want to stress for this case just the challenges, which I hope this school will help in solving. The idea of lack of cross-disciplinary interactions, fragmentations of standards, competition for talent and gender imbalance, unbalanced competitiveness within Europe, and the absence of bridges between labs and SMEs. So I would thank Ivor in this occasion also for bringing one or two excellent Croatian SMEs, which are really representative, I think, of innovation here. And it's a pleasure also to have Nicola following me with instead a discussion on what is done at Bosch, so a large multinational. And of course, these are challenges related to capacity building. There are also challenges related to the science. And the idea is that, well, materials are complex, as I discussed, and we get information about them through heterogeneous set of data. So a synthesis is generally a text with some scalars. Then we have images, which can be microscopy, or spectra, which can be coming from spectroscopy. And then we have key performance indicator extracted according to, for example, time series. So it's really a complex matter. And again, I think within this school we will give access and example on how to deal with this complexity. And of course, this complexity is also reflected in the quality of data. So many of us do simulations, experiments are in a sense describing more the reality of it, but come with a number of unknowns. Hence the need to bridge the gap between emulators and real data, and do so in a trustworthy manner through machine learning. This, in a sense, it's our hope that will bring us an understanding of structure-to-property relationship and provide us with a truly holistic understanding of the process structure-to-property pathway. How do we try to solve these challenges in practice? Well, there is a first working group which deals with standards and reproducibility, so making sure that all of us gather data and use workflows which are sensible and indeed reproducible. We leverage this data according to a set of representation and algorithms, as well as advanced multimodal and agentic approaches to make an impact indeed in the structure-process-property relationship across different domains. And of course, we want to train, communicate, and valorize the results within our community and the one next to us, which can benefit from this kind of innovation. We started in 25 from 17 different countries with a fair difference between young researchers, YRC, and the more experienced one. Unfortunately, the gender balance was somewhat representative of our community, and I think we are doing better in that area, as well as increasing the impact and the reach of our network. What I'm also very happy as the chair of the action is that a number of different expertises are really present. We have domain experts across different materials. We have people trained in artificial intelligence and computer science that are interested in applying their techniques to our field. And of course, chemistry and processing and so on and so forth are all available. And I think this is also the beauty, another beauty of this community here present. Many of you come from different groups, and I really encourage discussions to learn about what the others are doing, for example, also during the poster session. So what do we do also in practice? Well, we have a budget of roughly 600,000 euros over 4 years, and again, these are for building capacity and foster research coordination. So one thing that I want to advertise is this instrument, which is called the Short-Term Scientific Mission. And this is a funding you can use to travel to the lab of somebody else, or to bring a researcher in your lab for a limited amount of time to collaborate on a specific project. And Ivor is the coordinator of these kind of applications. So for any question, you can come to me or to him, but this is really an opportunity to expand your horizons while making an impact and using the budget of someone else rather than your PI. Another instrument that is relevant, especially for during conference season, is that we give access to some budget also to disseminate your results, as long as they are in the context of machine learning for materials and molecules. to other conferences not organized by us. This instrument is just for young researchers, so aged below 40, or for researchers affiliated with the country, shown in green. And well, insofar, there have been 2 fruitful general meetings, 2 schools. This is the second one, and I hope it will be as great as the one in Ljubljana, if not more. Some experts workshop, and as we funded 14 different collaborations across groups and 10 disseminations, exactly through the instruments I just described. The next event is in Ljubljana, 22-26 of September, where we host an AI for Material Science track within the AI for Science conference, and you're all invited to send your applications. And with this, I want to stress that, of course, we started roughly 1.5 years ago, and now we start seeing the first fruits of this. It's a bit biased, but me, Federico, Sangyu, Venkat, and Silvia just got accepted on Digital Discovery, a very nice overview of uncertainty methods for machine learning for materials. And I think soon our roadmap on digitalizing material science will be also published on Journal of Physics Materials. And probably tomorrow, Jonathan will also discuss a bit about open data and a fantastic work in that context. So with this, I would like to acknowledge all the people that contribute to the management of the action. Of course, it's not just me, but all these people here that take care of specific aspects. For participating and further info, I invite you to look at these 2 different websites. This is our own website. This is the one hosted in the COST network. And another thing I'd like to stress is that you indeed have access to our Memorandum of Understanding, so the document that really spells out all of our objectives, and is one of the few things in my life that I'm still happy of having written, notwithstanding a few years ago. So I think it's positive. And well, with this, I would like to thank you all for your attention.
I don't know if there is any question about this, but I think you can catch Kevin during the coffee break. Before I invite Martin, I have 2 things that I forgot. Probably I forgot more, but so one, well, I forgot now. One is, yeah, I know. So all the members of COST, especially those that are funded by COST, have to sign every day the list outside. Otherwise, we cannot pay you. This is the European funding rule. So don't forget every day to sign. The second one is I bought today some extension cords. If you don't manage with the current situation, let me know and we'll try to get some more. But I hope you can change from time to time and charge. But yeah, let me know if this doesn't work. Okay, with this said, I invite now Martin from our computing center that is going to show you what they do and how this is going to help us this week.
Good afternoon, everybody, and hello. I'm Martin Belovic. I'm from the University Computing Center, Srce, where I work in the department of Advanced Computing. Today I will present the role of Srce University Computing Center in supporting research through advanced computing. And this is presentation part of the event. I will walk you through what we do at CERCE to contribute that. So let me point. Okay, working. No. Yes. Nice. We have around 180 employees across 11 organization units and operate in 3 locations in Zagreb. The data center we have in 2 in Zagreb, 1 in Rijeka, 1 in Osijek, and 1 in Split. We also our mission is to support digital transformation across education, research, and business. So the main goal is supporting digital transformation, education, research, and business in the academic and science. We strongly promote open science and open education. We also build and operate national e-infrastructure and digital services. We have over 30 services for the needs of the academic and scientific community in Croatia. So CERCE supports open science through the data science life cycle. Here we can see that life cycle. So we start from some kind of problem. We have a problem, we have a program we need to solve. We want to learn more about some phenomena, some dynamics or anything, and we start from there. We then collect the data, everything we can collect, and we start to coding, programming, or something with that. Then we see that we don't have don't have a strong laptop or computer, so we need a better system to run these models of simulation. So for that purposes, we provide to research and scientists advanced computing resource. For that purposes, it's not only research that is needed, but only the education, support, monitoring the system, security of the system. So we need to secure, and also there is some kind of optimization because there is no unique system for that purpose. So the scientists do process this data, analyze, then they need to preserve this data. So the storage is needed. We provided with service PUH, that is storage and management data service. We also have a journal hub, that is Hrčak. So scientists need to publish and read some scientific papers. There is also a digital repository. And of course there's a Croatian research information system that we collect output the project, people, and system and stuff. So after that, scientists of research can reuse this data and start with new planning, and the cycle's complete. Oops. So advanced computing is critical resource for solving research problems that require a high computation power. And at CERCE, we provide access to our advanced computing infrastructure. It's open to publicly funded research project, institution, research, academic activities like thesis work, and teaching. So we currently provide through this school through our research for the lecture and practical sessions. So for now we have more than 312 projects and 770 users. In data science lifecycle, we run to some problem. We then make some program, and this computer program is like is set of instructions in programming language for computer to execute. So we then run this program, but it takes a lot of time. So it's not only the bigger system that matter; it's parallel computing. So the main goal is to use parallel computing to simulate and use multiple compute resources to solve some computation problem. So we have a problem, we divide it to some smaller problems or a subset of data. So we make instruction of this data and send it to processor to process. So here are some advantages of the parallelization. So it's significant speed up that run faster by using multiple processor. And of course, if you have big system like HPC, it's higher efficiency, so it's better utilization of that system and hardware resource. Some disadvantages of parallelization is a very complex development. So it's hard to design, debug, and maintain the program, but there is also a lot of application and software that scientists don't need to code, so they reuse it. And maybe if they want some parameterization and some subroutine or something, they can only do that thing and just code that thing. Don't need to code every software. And there is also a limited parallelism. So speed up is restricted by the serious portion of the program. So not every code, not every software is not capable of full parallelization. So SUPEC, in our center, SUPEC, we have HPC system named SUPEC. It's for advanced computing for our user system. It's intended for the execution of such tasks that user applications very high performance requirements. The power of this system is measured in flops. We have a system 1.25 petaflops. It's not big system, but it has 8,300 processor cores, 80 graphic processors, GPUs, and 32 terabytes of working memory. So this system is very dense, so it can be scaled very easily. In some bigger data center, they have many of these racks. And these racks also is needed. This system also need communication between the nodes, and they need larger storage data, fast and larger storage data, because these systems provides users, many users, working environment. So we have multiple nodes. It's for different workloads. So some workloads programs need some more computing power, CPUs. Some need more GPUs, and some need more memory. And lately we have some AI workloads. There is some special nodes for that. It's like system with very fast network speed, like DGX from the NVIDIA. Here is some specification of our system. And for these systems, like I said, it's very important for the HP system. It's very important to the network. For network, we have Slingshot. It's 200 gigabit network. It's low latency, high bandwidth network. Yes, and this system is very special. It's very hard for scientists and our user because it's multi-user system. So it's used by multiple users, and there's need to be special software installed, like scheduler system for the requirements for the users. So they need to reserve some resource. Then if there is enough resource, they can calculate. And if there is not enough, they go in queue. So there is special like job scheduler system on this system. On the other side, there is cloud computing like Vrancic. This service is established on resource for HTC workload intended for a wider set of user application and system that require a specific programming environment and significant processing and memory resource. So basically, if people cannot use and fully use HPC, they come to this resource. So it's very flexible. They can create virtual machines. They can get IP public address. They can use a lot of services. They can install and configure system as they like. So it's based on OpenStack. It's a cloud computing platform, and Ceph is for the storage. And we can see here specification. Also, we have some nodes for different workloads, like server with CPU, GPU, and large memory capacity. So that's national resource, but of course, if you really need a big resource, there is also Euro HPC systems. These systems is across the Europe. You can see the map in the bottom. There is a lot of national competence center. The point of that is the one-stop shop for the HPC. So there is a place where users from academia, scientific community, industry, and public administration get support in the application of the national European infrastructure of high-performance computing. So if you really need a big workload, if you have big workload and you need a lot of resource, then you can contact your national competence center for the appliance to the Euro HPC. So there is a little bit different for that system because there is a calls every few months, and you need to apply on these calls, and then maybe you get the resource. So for this school, we will use Jupyter. So it's web-based. Of course, you can use some other resource. You can use your laptop and virtual machines. But this is a web-based interactive computing platform. It's very easy to access. It's via web browser, so you can just type Jupyter search higher and access it. So it has EduGain login. It's very easy. So first you need to click on the invitation link provided in the email to access our platform. So the Jupyter is specially prepared for this school. So there is a lot of servers, but please click on the school machine learning for molecular and materials research. So it's last one. And of course, there is a GitHub repo for this school. now a little bit about Jupyter. So it's cloud-based computing. It's on the cloud-based computing branch. So we use the resource branch, which is cloud computing. It's based on the OpenStack and Ceph, like I said. This is the main resource. On this resource we built the Kubernetes. It's container orchestration system, and we use Zero2 Jupyter Hub, which is Helm chart for deploying Jupyter Hub. And here's some specification of the Jupyter lab. So if you log in with Edugain and select the server which is provided for this school, you get the container. So every user gets own container with the Ubuntu 24 image. Every user have a home partition with 40 gigabytes of space, and they have a multi-instance GPU because we don't have a lot of NVIDIA GPUs, so we multiplied every GPU to 1/7 of the GPU, so everyone get small part of the full GPU. So every instance, every server have 2 to 8 CPU cores, 16 to 24 gigabytes of RAM. That's depend of the load. If the load is higher, then user get lower resources, so we can get better utilization of the system. And there is also a cooling idle notebook servers. So if you idle for 30 minutes, your server will shut off. And but hopefully home partition is permanent, so you just start the Jupyter server and everything will be there. For the school, there is also a Conda package, Conda environment, which is prepared for the special for the school. It's package management system, so everything is ready for the lectures. Thank you for attention. If you have any question, we can maybe show maybe we can show the login to the Jupyter and show you some examples. Like, so you have a web server like Jupyter Search Hire. You can go there. You then log into Edugain credential in Prijava putem. It isn't English version, but you can click only button you see. So after that, you get this menu. Oh, yes, of course. I can show you again. Just a second. Okay. Okay, so I can log out. So here's the landing page of the Jupyter. Just click on the one button here. It's login with Edugain credential. So after the login with Edugain, we have some problems with some Edugain users because identity providers didn't give us enough data, enough attribute to link you with some users. So we're solving that problem. Hope we will find some solution for that. So after the login, you can select the school image server for this school, and then just start the server. And then after the few seconds, everything, I hope, will be ready. So here is after the starting, you will get the Jupyter Lab with everything prepared for this school, and I think that's it. And there is also, yeah, okay, let's see. So that's it. So there's one GPU you can use. And there's some, I think, Conda environments for the lecture.
Yeah, so first of all, maybe step by step, did everyone receive the invitation link? Okay, nobody is complaining. Okay, and can you raise your hands? How many of you have managed to log in here? I think that's quite a nice number. The rest of you, if you have issues, you can report them, and we can then help you. But also, yeah, since many people manage to log in, maybe you can also group up with somebody. Okay, and then after you log in, I guess everyone also received the link for this GitHub page, right? Okay, everyone got it. So kind of there is just one important thing you have to do after you log in. Can you maybe scroll down a bit, Martin? We go down. Okay, maybe a bit up. Yes, so this chapter 3. No, it's chapter 4 actually. Right? Yeah. Okay, here, this thing which is marked as important. So after you log in, you need to run these two commands in the terminal. So this is also, did anyone maybe experience issues with this? Did everyone more or less do it? Okay, again, no complaints, sounds great. And okay, and now for running the tutorials themselves, we can maybe now show. Maybe you didn't run the commands, right? Okay, let's maybe try.
Okay. Okay.
Yeah, you want me to?
Oh, yeah, you can.
Okay.
You just copy the codes.
Yeah. Okay. Okay, you can try to copy this too. Okay, možeš samo kopirati u termin.
Okay, okay.
Okay, this should now hopefully work. This step could take some time. I'm not sure if it will work if you copied it at the same time, though. Okay, maybe.
Yeah, I think I downloaded it maybe.
I think you have to. Did you already do it?
Yeah, maybe I can delete it.
Yes. ML. Yeah.
Koliko je taj git velik?
Mislim, dosta je on velik, ali
ćemo vidjeti. Možda na DDoS svi. Ne znam koliko je usera spojeno. Da, ali moguće da imam problem sa ako puno HP user istovremeno počne skidat, ali dobro, malo duže traje. Dobro, bolje sat nego na vrijeme predavanja. Da, malo duže traje. Do 50 usera skida.
Okay, it's possible that the network is maybe you have your home filled out, Martin. Okay, can you raise your hands, the people who managed to clone the repository? Okay, it's already, okay. Maybe if all the users try to clone at the same time, or many users try, then the network would be slow, but once it's cloned, it should be fine. So anyway, maybe I can try to log in mine to show.
Yeah, of course. I have, I didn't increase the disk size for myself, so I'm on the default 10 gigabytes of data. I think that's a problem. So I think, but every user have 40 gigabytes. You can check with like this. That's, but I think you have 40 gigabytes. So if you want to log in, you can log in. Okay. Ne bi trebao biti problem. Ako želiš. Opa. Da, cookies. Imamo ići na ovaj browser. Dobro, sad imamo vjerojatno problema jer je puno usera spojeno, pa možda glavni server ne vre pre ovo, ali bude vjerojatno sad skroz par sekundi, malo duže treba. Možda se ti radni uvjeti kad se spoje.
No. Okay, so we have now 15 minutes more or less before our first lecture comes. So if you have any problem, raise your hand. Martin, there is one there or things like that. So we intentionally left a bit of space to sort out any technical issues before we start with the first lecture. So Martin, can you try to look there?
Hello, hello. So we are trying to solve every little error here and there, but the number of errors is a bit too large with respect to the number of people that are familiar with the system. We will be starting soon. Don't hesitate to write an email either to me or Uri or Ivor or in Slack so that we know who has a problem and how to solve it before tomorrow. I must say, Nicola's talk, well, the first 45 minutes will be very scientific in nature. Also, the second half, it's going to be hands-on, which is a Google Colab. So as long as you have access to any Google Colab, I guess it will work anyway. This doesn't mean that we will not solve your problems, but the day of today is safe, so don't worry. And we will be starting at 45.
We are starting in 1 minute. Možeš unutra pa ćemo sad početi. Pa dobro, možda skupimo još. Dobro, budemo sredili.
You share? Why share?
What was
You are the chair of this session?
Yes, then we will talk about tomorrow and other days. But I will finish. Okay, I think we can start with the real stuff. So our first lecturer is Nicola Molinari. He's coming from Bosch in US, and he's also apparently associate in Harvard. So we are very glad to have you here, and you can start.
Right. I assume everyone can hear me pretty well because I'm kind of deafening myself. So thank you, Eva. Thank you, Kevin. Thank you, all the organizers, for inviting me. I think this is a great location. It's a great school, and I really like fostering collaborations and training next generation scientists. So as Ivo said, I currently work at Bosch, but you'll discover that working in industry, you cannot talk about what you want when you want all the time. So today I'm going to focus a little bit more on the work that I did while I was at Harvard as an associate, mainly because of that, but it's still very much relevant work. I'm going to start taking you to a journey about concentrated electrolytes. Those are that go in batteries. You want to put a lot of cations in order to have a high conductivity, but that has a lot of problems. I'll explain it to you. And that led me to closer and closer to the machine learning community within my group at Harvard. And then I'll talk a little bit more about Nequip and Allegro, which I assume quite a few of you might have heard about. And that's also what the tutorial later on will focus on. Okay, I don't normally put an agenda, but this is a relatively long talk, so here we are. I will do some self-advertisement at the top, quite shamelessly. But I think it's pretty important for all of you to engage in this sort of industry-led initiatives and introduce ionic liquids and their properties in this context of electrolytes, mainly via classical methods. And that's also something I want to make sure that comes across during my talk. Machine learning is a great tool, but it's not the tool for everything in life. Then I will move on from that towards what I did as a first data-driven approach, always in this field of concentrated electrolytes, where I developed a theory for conductivity that is a little bit less noisy than the standard theory. Then I'll give an overview about tools that we develop at Harvard, so Allegro and Nequip, as I earlier mentioned. And then I will move on to using those tools in some of the contexts that are actually needed in this class of materials. Okay, the shameless advertisement. I cannot see anything from here. Okay, so computational material science challenge. At Bosch, I'm leading this initiative, and I think it's great, of course. Basically, as you know, in modeling, the initial structure of your simulation takes a lot of what you can sample in the phase space, how accurate your simulation is going to be, and ultimately what kind of properties you're actually able to correctly reproduce. And hydration of crystal is extremely difficult. It's not quite clear which one is the lowest energy structure. So it's not quite clear from where you need to start your simulation from. And this as an array of applications and see. So for instance, cloud seeding, or atmospheric corrosion, complex alloys, barrier coatings, and stuff like this. So it would be great to organize a challenge for the community that's going to culminate at Psyche at the end of August, where basically we provide 100 testers for 3 chemistries together with the energy of the structures. We do not know if the lowest energy is within the structures or if the lowest energy is another structure. maybe very close to this one, maybe very far from this one. But we challenge the community to essentially use either classical methods like genetic algorithms, or more, genetic-based tools like the one developed by Microsoft, for instance, to come up with structures that potentially have a lower energy. We're not going to tell you how we compute the energy because we want to avoid brute forcing the solution. That would break the spirit of the competition, I would say. But maybe the more interesting thing is that you can submit your solutions and we're going to rank them, and then we're going to rank the participants, of course. And the up is for this challenge. So, of course, the most trivial and maybe boring one is a certificate, whatever. But then we'll give the winners a chance to present their findings and their methods, and they're brainstorming the letter of the solution to the internal Bosch community. And for those of you that don't know, Bosch actually has an amazing research team. So we are like 1,500 people with PhDs doing actual fairly fundamental science. So showcasing what you did to this kind of audience will bring a lot of nice things to you, a lot of feedback, and also potentially maybe job opportunities down the line. And also, as cherry on top of the cherry cherry season, the top 3 participants will be invited to the final round for internship in our Boston office, which is actually very competitive, and I did in the office, and it was great. So I only have good things to talk about. If you want to learn more, of course, there is a website. This is the QR code. Scan it. I don't know if the presentation is going to be available or not, but ask me and I can point you in the right direction. And, just shamelessly submit your solutions and we'll see where it goes. Okay, on to the actual talk, I would say. Searching for next generation electrolytes. So as I mentioned, electrolytes are essentially the material that you put between the two they have quite a few technical requirements that they have. The most obvious one is that they shouldn't allow the two electrodes to short circuit each other. So to have very, very poor electrical conductivity. At the same time, you want them to have a very, very good ionic conductivity because you want to essentially rebalance the electrons that go in the outside circuit to power your light bulb or whatever you're powering. Aside from that, you want them to have excellent thermal and chemical stability. You want them to be non-flammable or flame retardant. And you want to avoid situations like this that are suboptimal. And the issue here is that when you put a lot of ions to have conductivity, to have high conductivity, and that's because you want to charge your battery very fast. For instance, you don't want to stick your car in a power station for like 3 hours, right? When you do that, class of materials that have the first two properties show essentially very, very high viscosity, and that also translates to very, very slow ionic conductivity. So essentially, you number of ions, hoping that there are more charge carriers, but then you decrease their mobility, so the overall conductivity goes down. MD simulations are a great tool to investigate these sort of things. Diffusion, ionic diffusion is by nature basically a molecular level property. And that's what I did for quite a lot of time of my career, actually. And let me introduce you to a quantity that is going to be kind of important going forward. So it's better that you guys have a rough understanding of what that is. And that's this K. It's called transverse number. Think of it as very easily the fraction of ionic conductivity that is carried by the cation of interest. So the total conductivity, if you have a salt dispersed in a polymer or in a water, is going to be the diffusion times the charge essentially of the positive ion, but also of the negative ion. But that's not the conductivity that you care about. The conductivity you care about is the one by lithium, for instance, in a lithium-ion battery, which is the carrier between the two electrodes. So what you define essentially is the part of the conductivity that's carried by the cation of interest, quite often lithium, but it could be calcium and other things, divided by the total conductivity. So you want this number as high as possible, of course. Of course, the limit is 1, and you will see that surprisingly, you actually can go negative in this number, and that's, of course, really bad. Okay, so what do we did classically in this field? I decided to look at a bunch of ionic liquids because I have very, very interesting properties, as I mentioned at the beginning, and see as a function of concentration what kind of transference number they get. And I was triggered by an experimental group that did this kind of measurements with a novel experimental technique that actually allows them to measure created solution theory diffusions rather than the dilute limit diffusions, and they found negative transference number, which is possible, but it's very, very rare. So it's very, very interesting for someone like me to look into. So since I have access to computers, I can very easily make a heat map like this, where on the x-axis, I have a bunch of anions. The cations is going to be lithium. A bunch of different loadings of your electrolyte. So think of it as literally amount of salt that you can disperse in your material. And the color and the numbers are the transference number. Blue is negative, red is positive. And as you can see, the numbers, are kind of around the place, but trend. So at low concentrations, you have a negative transference number. At high concentration, you approach very, very high transference numbers. So, of course, this is extremely interesting. A little bit more into this. So, like, what is the origin of this anomaly? And essentially, you find two things. The first one is, so it's a system dispersed in another ionic system, so you tend to make clusters, and these clusters are asymmetric. So there is the ionic liquid is normally an organic cation, which is not useful for battery operations or fuel cells operation or whatever, and an anion, and then you normally put in the same anion with lithium or calcium or the cation that are the cation of interest. So you can still maintain charge and neutrality while at the same time have asymmetric lithium clusters. By asymmetric, I mean there are more anion in the cluster than cation. So the net charge of the cluster is going to be negative. And here you see different loadings on the three subsequent plots. And on the y-axis is the number of anions in the cluster. The diagonal line that I plot here is the equal charge cluster, so same number of ions in the cluster, and you can see that going from 0.4 to 0.5 to 0.6, which is actually you're going from negative to positive, but there is quite a different population of cluster in your system. So you go from having essentially all negative clusters, because they are above this line, to having a single essentially system percolating cluster in your system. And this should be the first hint of what's going on. The second thing is, okay, there are clusters, how do they move? Because if you think carefully, I told you that the transference number is the fraction of charge carried by the cation of interest. But if you surround this cation of interest with two negative charges, then you start essentially listing to the numerator, and that's how you get into the negative domain. But this cluster need to exist for a non-trivial amount of time, because if they dissolve in the system immediately, they're not real clusters, this effect is not going to be there. So you need to compute, well, I came up with this measure, which is essentially a fraction of time that these clusters exist together. You can see that at least 40% of these clusters have a persistent time of over 2 nanoseconds. I don't know if any of you has done this like kind of diffusive simulations, but 2 nanoseconds is actually a pretty long time for a cluster to exist in this field. Okay. Then this next question, and this is also triggered by experiments, because they were actually able to measure the effective charge, and the effective charge is again the charge of the cluster. So the cluster is maybe 3 anions, 2 cations, so as a net charge of -1. In experiments, they developed this electrophoretic NMR. It's a fairly complicated way to measure mobilities that actually can come up with an estimate of the cluster size, an estimate of the correlated transference number, as opposed to the classic way to measure diffusion constants, which is pulse field gradient NMR. Okay. So from theory, I decided, okay, let's make our own version of the effective charge. So it has some sort of diffusion here, some sort of time scale of existence, some sort of correlation between ions, and this is what I came up with. So the red dots here are my simulations, and the black squares here are from this paper. Maria Schonhoff, she's in Germany. She does this electrophoretic NMR experiments, and as you can see, there is actually, they're not able to measure the whole curve. The reason is pretty easy, as I said. If the more salt you put in the system, the higher is the viscosity. The higher is the viscosity, difficult it is to do this experiment. So they're limited to fairly low loadings of the electrolytes. But you see very clearly that the effective charge from experiments traces extremely well the effective charge of the computation. And the final solution is the one that I spoiled at the beginning, essentially. So you have the lithium that should move in one direction, essentially, but since surrounded by more anions as a negative effective charge, so it's moving in the so-called wrong direction. And, you know, this is the real power of automation, because now you understand what's happening. So you can think of, okay, how can I solve this problem? Well, key design principles I can come up with to avoid, for instance, persistency of this cluster or having negative clusters in the first place. So the first criteria would be, you can, well, I basically already said it, decrease the asymmetry. So clusters that are more balanced, or maybe have no negative clusters at all. And then decrease the persistency of the cluster. So the idea that I had was essentially, and this was the first instance of maybe data mining a little bit in my mind, the way I came up with this. But essentially, there are these molecules, ionophores or chelators, for the chemists in the room. I'm not a chemist, so I'm just repeating what I read on papers. But essentially, they love certain types of atoms, and they're very selective towards those. And the reason is there is some essentially steric hindrance in these loops, as you can imagine. So I thought, okay, great, I can do calculations. What happens if I do those calculations, including this or different types of this in the calculation itself? So here, n in this plot is the number of ionophores. The more you add, the more you break. In my mind, the more you add to break the asymmetry, because this will coordinate preferentially with lithium in this case, rather than coordinating with lithium. And crucially, this as a zero net charge, so you're not creating more negative clusters. And at the same time, then you will have what the mobility is of this cluster at this point, because it's true, now you have a maybe positive cluster, but what if it doesn't move? It wouldn't be useful either way, right? But what you can see is that adding more of these ionophores, you go from the situation I was explaining before, so a lot of clusters above this line, to clusters that are way closer to this diagonal line of equal charge, and a lot of also on the other side of this diagonal line, which is great. So I concluded, good, the ionophores decrease the cluster asymmetry. And then we can look at the persistence time, which is the one I talked about in the previous slide, and you can see that the persistence adding this ionophores goes down. And again, this is the basically number of nanoseconds, let's say, that the cluster exists together. So if you decrease this time, the cluster will break apart easier. So you have less clusters that maybe are negative, contributing actively to the conductivity. Okay, what happens? What are the technological consequences? So as I said, okay, you break the border if it doesn't move. So you need to plot the transference number, but also the conductivity. I don't know if I have it in this slide. I don't. But the conductivity also went compared to the base case. And the transference number goes from negative here to positive. And crucially, you saturate. It's fairly easy to imagine why you saturate, right? Because you have a certain immune system, let's say 150, whatever, I don't remember. But if you add 150 ionophores, those ionophores are going to attack the lithium, let's say, but the 151st, that's not going to do anything good to the system. So your contribution from the ionophores actually saturates, and crucially, it brings the transference number to positive. And I did this first, and then Maria from Germany decided to do an experiment. So she didn't have access to the ionophores I used, but she had access to other ones. You can clearly see there is a pattern here. So like basically the 4-oxygen was the best one. Essentially, you know, it's the perfect size to wrap around the lithium. So it's very similar to the one I had used that actually was cyclic. But here, go down this line, essentially you increase the strength of the chelation, so the strength of this molecule to stay together with lithium. And the black one is the base. No, these molecules are introduced. As you can see, the transference number in the case, so focus on this one, which is the lithium cation of interest. The black one is the lowest one, and it's in the negative territory. And the more you add of strength of collation, the more you move towards the positive, even crossing this barrier. And honestly, this is the maybe time in my research career I felt really good, because I was able to predict a technology relevant phenomena before experiments, and I was able to file a patent on this while still in academia. So I was very pleased with myself, as much as you can be, I guess. But let's move on now. The next, which is maybe a step in the right direction for this conference, which is how do we leverage the incredible amount of data that you actually produce in this sort of simulations to maybe become a theory that is a little bit better than what we had around for, like, I don't know, 100 years or so. This is a not so scary looking, I guess, as equations go. It's fairly complicated, so I'll break it down for you. But as I mentioned at the beginning, essentially you, well, let's maybe, well, I already introduced that. So this is the conductivity. You want to increase this as much as possible for technology purposes. You want to charge your battery pretty fast. You have a prefactor that has kind of the usual meaning here, is not particularly interesting. But what's interesting instead is essentially there's a matrix. This matrix is called the correlation matrix of the system. And as you can see, you have all the vectors essentially point, your ions that move around in your system. And what you want to do is essentially take the slope of this matrix over time for as long as time as you probably can, because you want essentially that relation to kind of scale linearly, exponentially with the, with exponent equal to 1 to converge your simulation essentially. If we focus on this quantity, it's a matrix, so we can plot it, thankfully. You have essentially diagonal elements. And focus on when you do uncorrelated simulations. You say, okay, all my ions, let's say that your ions of interest are species A, all my ions do not talk to each other. It's off the diagonal is 0, or if it's not 0, I just ignore it. And if that is the case, you essentially have completely independent diffusing particles in your system, and you can say, I can just take the average. So your simulation converges really fast because you can have as many ions as you want in your system, so you can average over many trajectories, essentially, independent trajectories. The issue is that what's on the off diagonal is really important for concentrated electrolytes. It is what brings you to the negative transverse number territory, as discussed earlier, is the correlation between ions. So what we'll be doing instead is looking at this matrix as blocks, of course. So species A, so let's say lithium is lithium-lithium block. You would have the diagonal. But then lithium-lithium correlation, the lithium anion 1 correlation, the lithium anion 2, or the cation 2, whatever that is. When you do this, the issue is that you cannot count individual moving species as independent, and you need to look at essentially the center of mass of the entire system and how it moves. That, of course, is way noisier, and it weighs lower because of that. The idea behind what we can do about this is essentially in your simulation, things happen not in a run. It's like if you look at the matrix, there must be a way to understand, I call them eigenmodes of diffusion, in order to use those eigenmodes of diffusion to diagonalize that matrix. And if you have all the modes of diffusion, those that eigenbase should be complete. And if it is complete, everything after the diagonalization is diagonal. So everything that's on the off diagonal should be 0. So you start with a matrix like this. You have your eigenbase of diffusion. You go in a situation like this, which hopefully is diagonal heavy as it gets. And then you have essentially noise of the diagonal, because remember, we think we have the modes of diffusion, so we can rotate that matrix in a diagonal. So what I did was, okay, everything off diagonal is 0, because everything on diagonal should be noise at this point. And of course, when you do something like this, you need to check that what you're setting to 0 is, so is it centered around 0? Is it looking random? Is it random looking? So I did this. Here you look different systems, and this aberration is a measure of correlation. Let's not focus on that. Essentially, you see that it's centered around 0, and this, of course, is really important because it means that your method doesn't bias your solution. And then what you can do is that you can rotate this matrix back, the same eigenbase, and get this matrix, and then you can put back into your equation and have a so-called denoised measure of the conductivity, as I call it. What are the key takeaways of the approach? So let's not go too much into details. I think you're going to be more interested in the second part of the talk, but I think I really like you can apply this method without knowing what is the correlation of your system, because we proved that even if your correlation in your system is not as relevant as you might have thought, you don't your conductivity estimate, both in terms of like absolute value, but also in terms of convergence time, essentially. And then I spoke about those eigenmodes of diffusion. Small test, of course, if the system is big, it's impossible to disentangle. But I did a small test where I put like a dumbbell and like a, I don't know how this would be called, but like a triangle with springs together, and I let them diffuse in a bath of other things. And I didn't tell the system that those things were moving together. These two particles were moving together, or these three particles were moving together. And I looked at what it was picking up in terms of eigenmodes of diffusion. And you get essentially two types of vectors. The first one are the important ones. So these are the normalized 1, 1, 0, 0, 0, 1, 1, 1. And this essentially tell you that there's two move together, there's three move together. And then you get this, which are the rotations. So these things rotate in place. Is not important for your diffusion. That doesn't contribute to conductivity. And this is essentially how this model, the method, the theory picks up and denoises the trajectory. And then, of course, I had to apply it to a real system. And I looked at two systems, one with correlation factor below one with correlation factor. Those are essentially two different types of correlation. So it's important to check both of them. Here, the green box is the conductivity, as mostly I would say everyone does it, assuming the correlation in your system, and it's off. So this ratio is essentially the ratio of the real conductivity versus the decorrelated one, and that's why it's not 1. And then my method, right now I don't remember which color it is. So the blue one is my method. The red one is the the theory of concentrated electrolytes, and you see that essentially it reproduces the absolute value essentially perfectly. And also, the uncertainty of the conductivity is actually much lower. And there's a hint for what you can do with this method as well. But as you can see from the actual plots, the noise is much smaller. Oh, okay. No, and then I'll say one more thing about this, the next thing else. The nice thing about this method, then, since you are decreasing the uncertainty of your estimation because you're denoising your trajectory, what I did here was essentially applying the method on trajectory length as the full method, so that will have a higher uncertainty. But I mean, normally when I make simulation, when I set up simulations, I have a level of uncertainty I'm comfortable with. Below that level, I'm like, okay, I'm gonna start the simulation. So since I reach low uncertainty much faster with my theory, I can run shorter simulations. And that's a really exciting way of how you can, because conductivity measurements are really long, even on a computer. You need to reach long time scales. And if you can cut down by a factor of 5 or 10 your compute time, like it would be in this case, that's great news in terms of like computational resources. Okay, machine learning potentials. I'm not quite what's the background of this audience, so I started maybe early as possible, and then I'm going to give you kind of a broad overview, but I like to think of myself as fairly approachable, so feel free to ask both after the talk and during the coffee break or the next few days. But essentially, the very basics, it would be these. So what we do is relatively simple. So we have balls on a computer. They have some properties. We call these balls atoms. They have positions. And then physics tells us there is a potential energy surface that we can differentiate to the positions of these balls. And that gets us the gradient for the forces, essentially. Then you can integrate the equation of motions via Newton, and you can update our positions based on a time step and Newton's equation, essentially. And there are a few ways you can do this. So one is density functional theory. In this case, essentially, you treat your system fully, I would say. There are better ways to treat your system, but this is full enough. So there are ions and there are electrons, and those are treated explicitly or semi-explicitly. And generally, you have a high accuracy, but fairly low speed. and not only system-wise, also the size of the system is fairly limited. Then you have classical force fields, which is, my area mostly. That's where I started. These are rigidly parameterized functional forms. They are very fast because they are, they actually have a function and you just ping, so it's pretty fast. The reason, the problem is that they are just interpolated over vast chemistries and is somewhat questionable. So you need to, know exactly what you're doing, not to mess up too badly. But the good thing about these ones is that they're fast. So since you're just pinging a function, you can do this many times a second. And then recently, or maybe not so recently anymore, but like we started to focus on bringing these two together with the power of machine learning. So you look at this potential energy function and you say, okay, I need a function that I don't know how it looks like, but that reproduces this to a reasonable degree of accuracy. What can I do? I apply an interpolator, machine learning, to high accuracy data, density functional theory, to then sample a speed relatively close to classical force fields. So the goal here is essentially to learn what we call an equivariant representation of your potential energy surface, essentially the geometric features and chemistry information on the type of atoms, of course, as you can see here. What are the physical symmetry? So the reason why this slide is here is because it kind of shows that if you put a little bit of thinking in what you're doing, it's better. End up using less data, less compute resources, less energy, and everything. So the issue here is that this is not maybe a new thing of what we were trying to do, but other people did it in invariant way. So just looking at distances, for instance. And the easy way to think about this is through images. So if you think about, you want a network that recognizes a cat. Okay, a bunch of images of a cat, and then the network recognizes the cat. But then you turn the picture, and then the network is like, I don't know what this is anymore. So what you can do is data dump your model, provide all the rotations of your cat to the model, and hopefully the model will learn that if you rotate an image, it's still a cat. Or you can say, well, cat up to rotations. In physics, we have the Euclidean group that governs the sort of questions in the real space. So we essentially want rotations to be taken into account. So how is the energy of my system if I rotate my system? The same. How is my force if I rotate my system? The same in modular changes. You want inversion, and that's the O3 group. And then the Euclidean group gets into the equation if you add translation. And then, but this is relatively easy. All the networks at this time had the permutation symmetry. And these are the two things we came up with. I was particularly involved with one of them. I was kind of of the other one. But these are essentially networks that respect the Euclidean symmetry. And as you will see later, that translates to much fewer data needed to train the model and much faster as well. But essentially, you treat your features as equivariant. So they rotate with the symmetries, as I said. The basis turns out to be a spherical harmonics. I guess we were physicists, so it has to be a spherical harmonics. And your quantities are tensors rather than vectors. One important thing is that the big leap between Nequip and Allegro is that Nequip, it's horribly to scale in space. And that's because it's a message passing neural network. Message passing neural network means that if you ask your network to have 4 layers and the cutoff is 5 angstrom, then you have all of a sudden the angstrom of interaction between atoms, and that's completely unscalable on a supercomputer. The good thing about Allegro is that it retains basically the same accuracy as Nequip you have to give, but it's strictly local. It focuses on the edges in the network, and that allows to essentially avoid this passing structure, and then you end up with a purely local model that doesn't have this horrible scaling features with respect to the system size. So here you see, this is now an old comparison. I had to take it from the old paper, but With 1,000 fewer data, you learn properties. I think these are force MAEs on water, different phases of water, and compared to, I mean, no shaming. It's just first generation machine learning potential. Here there are no symmetries, and they train on a tonal structure, so they rotate it carefully, and they get to these errors. We train on a factor of 1,000 fewer structures, and we get errors that are better than these ones. Physics. And then comparisons, but they all follow the same logic. We encoded the right symmetries in your system. You need fewer data. You need fewer data to learn them. You don't have to learn them. And then, you know, what do you do with this? You start testing the structural properties of your system. So one would be the radial distribution function, which you will actually a model and test it in the tutorial after the coffee break. Not of this system, but another one. And the angular distribution function. And you see that, you know, compared to, which is, you know, the DFT way of doing things, you have perfect, you know, tracing of the curve. So you did pretty good. And, you know, you can come out with statement like that, train the system at 300K, and we were able to reproduce this at 600. I would argue there's a lot of luck, so I don't fully trust extrapolation, although you could argue it's interpolation of your training set here, because higher temperature samples the phase space in a broader way. This is pretty impressive, I would say. And then you move on, you graduate to the difficult properties, which are the dynamic ones. And here, you know, diffusion person. So I looked at the diffusion coefficient, again, AMD versus the machine learning potential for both AltenQuip and Allegro. Different systems. The slope one here is the target slope. So you stop your simulation when a bunch of your simulation time is at this slope. And you can see that AMD and Nequip or Allegro are essentially indistinguishable, especially within uncertainty. I don't know how I'm doing with time, but then you know, if you have GPUs, Allegro is very, very scalable, very, very decently. So here we had a bunch of GPUs, and we were able to simulate 100 million atoms. Is it useful? I don't know, but it's big and it's nice. And then you apply to Summit, and you have access to, I think, 27,000 or 28,000 GPUs, and you can do 500 billion simulation atoms simulation. Here, the video is not going. But essentially, this is an application probably very close to Kevin, our organizer, Catalyst. So you have hydrogen in the gas, and the surface splits, and then stays on the surface or does whatever it wants to do. But you can use sort of simulation to speed up collecting statistics for instance, what's the reaction mechanism and stuff like this. And there are simulations that maybe you could argue the simulation doesn't need this many atoms. You can do the same in parallel. But what about dislocation folds, or like edge dislocation gliding in a material? You want to simulate the actual grain boundary effect, reflection of such a dislocation. At that point, you do need big simulations because the stress field has very, very long correlation length scales. Then, as I promised, merging the two parts of the talk, going ML to my dear friends, the ionic liquid electrolytes. So here is kind of, because there are quite a few questions that are not necessarily addressed by the foundation papers on machine learning. For instance, how does it deal with strongly ionic systems? And do to train such models, because electrolytes, normally you want to test different concentrations of the cation of interest. And to do that, you introduce different environments that I talked about earlier. And if you do that, how many of the structures you need to sample to make sure that your network actually is able to correctly capture all the entropy eventually. So we applied these methods, Allegro and Nequip, to these problems. This is the example electrolyte of that we picked. Lithium is the cation, Me plus is the organic cation for the ionic liquid, and PF6 is the anion. Okay, this is like a plot. I love to make these plots. Here you see essentially, okay, let's start from the top. 0 is pure ionic liquid, so you have no salt in the solution, essentially. So this would not be an electrolyte. 1 is pure salt, so it's like, salt. So here you also electrolyte. Your electrolyte is somewhere in between. So the fraction here is the fraction of salt in the pure ionic liquid. The left side of the plot is versus MAEs in milliV per angstrom, and the right side is the energy in milliV. Generally speaking, blue is good, red is bad, and the triangles are the concentrations at which I train the potential. So naturally, the first thing I did was try what you would call the high entropy mixing states, which are the close to the center, and forces degrade, energies degrade. And I was like, okay, let's try. So basically, the pure systems. Quite interestingly, it still does pretty well. There is a degeneracy as a function of going away from the pure state of the pure ionic liquid, and that's because you're not sampling those interactions very effectively, essentially. But it's still pretty good. Energy is the same. And then I tried 3 all on one side, 2 all on one side, good. 1, okay, can we do it with 1? Forces, yes. You can probably imagine why. So you have a lot of instances of calorimetries even in one concentration, so you can sample depth pretty effectively. So every atom has a vector there. But if you look at energies, that's a system level quantity. So if one training point in the concentration range, your extrapolation power is 0. That was an equip. We did the same with, I would say that there is not much to say here, except they work very, very similarly. So here we're focusing on the energies. You see, which is the problematic one. You see that the range, but the trend is essentially the same. So one concentration, energy, non-extrapolable. Okay, same research process. It turns out it's relatively simple, but it's a useful test case because it kind of teaches you how you have to train these sort of things. So if you have one concentration, you essentially 3 unknowns, 1 equation, and 1 constraint, charge neutrality. And so your system is underdetermined. So you essentially pick the energy for whatever concentration you trained on, but the slope of this curve is completely messed up. Essentially, you're not learning the chemical potential of your system. So if I add an ion, you don't learn that with 1 concentration. If you add at least two, what you end up doing is you end up making these equations solvable, and you can essentially the chemical potential dependency here with respect to DFT, as you can see very well. If you train on 3 compositions, we saw that it didn't really improve anything. And that's because you essentially learned enough about it. You, of course, need to be careful choosing maybe the high entropy parts of your concentrations. Again, maybe avoiding the extremes. But if you do so, it works pretty well. To come up, we tested this on a bunch of our calculations and on a bunch of people that we knew were training this sort of systems. We gave them this a golden rule, which is C is the number of unique compositions you need to sample, N is the components of your system, and M is the number of constraints, and that gives you C, how many you need to sample. Okay, then we started to look at something real. So this ionic liquid is useful for, I cannot fully talk about, but essentially its oxygen solubility is really important. And it's not part of this talk, but if you want to measure solubility, it's really important because it's essentially you need to compute the excess chemical potential, which is the excess energy of putting an oxygen, in this case, into your system, and that is an quality. So if you have a quantity, so if you have a small error there, you're doing very poorly. So the first step is, can we apply the systems here? So this is the ionic liquid. We were collaborating with an experimental group, so we also have measurements here. And this slide is essentially to give you a feeling of what kind of training procedures you need to go through to have, but I'm happy to talk more about this after the talk. We started by sampling classical MD for the geometry of your system. That turned out a bad thing to do. Essentially, you have a lot of misalignments in the configurational space. You have a lot of misalignment in your configurational space that if you just do a single point energy, you just end up sampling the wrong, equilibrium distances, the equilibrium angles, and such like that, and it's impossible. What works fairly well is if you do this, because it's important, because you related structures much more easily with classical force fields, and then you do a shorter AMD run after that on each of those sample structures, what you end up is with a parity plot that looks like this, so much better. And then we were interested in essentially fitting an equation of state to this data. So we needed different volume scans, train a model, did some sort of volume scans, and then put those structures back into the DFT engine for computing the training data. And as you can see, you have energy and the parity plot of the energy as well. There is a difference. The difference is actually very small. If you look at the scale, we're talking about millivip atoms. The top one is the dynamics. So as a function of the trajectory goes, we resample DFT and see how much different we are. And the difference here crucially stays roughly the same. So the system is not degenerating energy error. And that's a very important thing for this sort of things. And then we decided to look at the density via the Tate equation. So the equation of state I was talking about. Horrible, but it's not that bad. So if you look at the scale, you're actually fairly within classical uncertainties of classical molecular dynamics. The dots here are the classical force fields. You could argue why you're using a molecular dynamics here if the classical force field is so good. The reason is because this classical force field has been by me to do this essentially. So I don't know if you're familiar with this field, but quite often you essentially rescale the atomic charges to get rid of some polarizable effects. And if you don't do that, this is how the energy, this is how the density as a function of temperature, as a function of concentration looks like. So it looks good just because I try to make it possible. But more crucially, if we look at different properties, density, thermal expansion, and isothermal compressibility, you see that we're actually fairly close. And we show that most of these differences are actually due to the flavor of DFT that we chose. So there is this quantity exchange correlation functional in DFT that is a pain. So you can go accurate, but then it's much more expensive. So we're working towards a way of making the sampling of the phase space even more efficient so that we can use higher accuracy methods to get rid of some of this DFT. And that is the end of my presentation and the end of my time, I think. So I'll happily take any questions. And otherwise, thank you for listening.
Thank you very much. So if there is some, hopefully short, take them now, or we have quite long coffee break, so you can also take them. Yeah, I'll have to, maybe you can answer here because I have to take microphone, otherwise online we won't hear anything.
Thank you. Hi, thank you so much for the very comprehensive presentation. It was really good. I just wanted to ask a question because I'm kind of dealing with a problem. I'm working with liquids and solids and the interfaces and the melting points, and I also got some results like from the machine learning potential that quite in line with experimental data, and I kind of wanted to ask like, how do you know which components are of the error are coming from DFT functional, and which ones are actually, maybe training that did not go well, and how to choose the right density functional theory functional to do this?
Hello? Can you hear me? You're not asking an easy question here. So let's start with the last part, which is the functional exchange correlation part. That's empirical, right? So you need to test a bunch and come up with the lowest level of theory that allows you to do and sample the reaction that you're interested in, right? So I'm a big fan of you don't need to get everything right. You need to get right what you care about. So if you try, when I set up this, make a list of the reactions, and I'm not talking reaction in a chemical way. I'm like the processes that I want my simulations to reproduce, and then when I have the first iteration of specific test on those quantities. So if I want to simulate diffusivity, for instance, I look at diffusivity explicitly. And then you need to start looking at dynamical quantities than the static ones. So in the community of machine learning, it's quite quite often they focus on the single set of snapshots without looking at dynamic trends. So like, is the error increasing over time? Do you get unphysical phenomena popping up? Is the uncertainty of your model constant? The sort of dynamic questions I call that are important to look at when you kind of train these models. And in my experience, the first machine learning model that you train is never the correct one. I always use the first ground on top of which building an actual production-ready model. Does that answer your question?
Hi. The training earlier, so you have the two states on the scale. Is saying when you said like 3 is yeah. So how do you know where on the scale to have your representative composition sweet spot to training it?
Yeah, so in this case, I would focus on the essentially what I call high entropy states, which are the central ones, because essentially this is a mixture, right? So you're mixing different things. Locally, you have quite a bit of variability in terms of like what comes next to what, right? So if you go to the extremes, you will have much fewer of those unique interactions if you go to entropy in the system. Yeah. So that's kind of the reasoning I had behind this.
So is there also like a minimum sort of composition distance between the two to get a good slope?
I mean, you can probably compute that because you can literally compute the number of states that you have in your system with given geometry. There is an optimum. I don't think you need to stress them much about that because, if you're worried about that, just run your simulation 5% longer, 10% longer, As long as you're in a good mix, you should be able to sample the relevant geometries. Okay.
Any other question? Federico, you are the last.
I have a question about the first part of your presentation, and it's about the importance of the reference frame in which you take the simulation, especially if we frame everything the Green-Kubo formulation. I really don't understand in general the partition of the total conductivity into single contributions. Not really here, at the very beginning, when you spoke about the what's the name?
Number.
Yes. Mm-hmm. And the first equation that you showed was in terms of a partitioning of different terms. But if I think of a really simple system, like a molten salt, and I fix the reference frame on one of the two species that are diffusing, I get, I think, in one case 1, and the other case versa, depending on this. Right. So I was wondering what's the rationale in this?
This is a very electrolyte-heavy question. But I think the real answer is that there is no correct frame of reference. So especially if you go to concentrated solution theory, there is no such a thing as correct frame of reference. You could use a momentum-based reference, you can use a mass-based reference, you can use a geometric-based reference. The normal way of doing it is focusing on what you have as a source. So I'm fairly familiar with polymer electrolytes as well. In that case, the polymer is by mass the majority of the system, and by volume, the majority of the system, frame of reference of the polymer, that doesn't create problems, and that the numbers you get are relevant. But yes, in principle, you can sit on the anion.
That's in principle arbitrary.
Yeah, it is a way of doing it.
Because the nice thing about the global formula is that is invariant with respect to the reference frame. So the green Kubo formula, if you photo, that is invariant. If you add the Galilean transformation.
Yeah, but because you're looking at the whole matrix.
The
problem with the transference number is then you end up picking, right? Because you're picking.
Exactly.
And
that's something.
That's you give up the invariance with respect to frame of reference.
Thank you. I hope coffee is waiting for us. So let's finish this session and thank Nicola again once again.
Thank you.
Okay, time for tutorial. Okay, first thank you for keeping the schedule. I'm surprised that you went back to the room on your own. Doesn't happen often on the conferences. Okay, so we have now tutorial. Before that, let me remind you that we have a city tour. It's going to start at 5:15 in front of the building. We are going to split in 2 groups, and then each group will have their own guide, and we'll go to the city center. But before that, we have a tutorial kindly prepared by Nicola. So I think you are ready to start now. Okay. Here I will help you. Okay.
Too dark. No, you know. Oh. Is it working? Yeah. Can someone at the back tell me if they can see properly the writings or? Well, but maybe they want to see what I'm doing. Yeah. Okay. We good? All right. So I set up this tutorial to guide you through a kind of a mock exercise in how to train a machine learning potential with Nequip and Allegro. We're gonna go through the tutorial of the Git repo itself, and then we're gonna start looking at what parameters matter and how they influence the learning, what kind of errors do we get, and then after that, I think we pre-compile lumps to work with per Allegro, so it should work fairly smoothly, and we'll do an actual training for an actual material, so silicon it will be, and we'll do the pair distribution function of silicon. So first of all, has anyone in the room trained Nequip or Allegro in the past? Okay, some, but not many. So, you know, Allegro and Nequip are both fairly, maybe not state-of-the-art anymore, but like very, very close to state-of-the-art models to do machine learning molecular dynamics that I showed in the presentation. So you should enjoy this. So you have access to the notebook, so you can rerun it anytime you want. You can ask me any questions you want. Also the paper references and such. But this was originally a collab, so hopefully it works smoothly. But maybe something I didn't quite talk to about doing my talk, which is what's the procedure to train such potentials? So like what are the steps to get to a model that then you can actually use to do physics with? So the first thing is data generation, actually. So that's the stuff that doesn't have, in principle, anything to do with machine learning. So that's where you would use your DFT. And then you go to train. Train is a black magic sort of art. So there are a lot of parameters that you wouldn't guess they're important, but they are important. And ones that you would guess they're important, they don't matter at all. Then you need to deploy. Deploy is the technical term that you use to, say, compile a model to essentially make it static, and then use it, and then running in your favorite MD code that should be lumps, the model itself. So let's start with, first of all, everyone is logged in, everything is fine, were you able to clone the Git repo? Okay, noise is, and lack of noise is acceptance. Okay. How? I don't. Here. Okay, so the first two cells don't do anything really. I didn't set up 1B, but weights and biases, so 1B is a way to track your simulations kind of automatically online. Enlarge. Okay, please give feedback if you don't see or anything. So weights and biases is a free for academics online platform. NeQuip and Allegro are set up to communicate with it from your cluster. It's actually very nice. You can track essentially learning curves or basically training metrics on the fly. So you can log in from your phone if you want to, and then kill your simulation if achieve whatever accuracy you wanted or such. So I wanted to put it here just for knowledge essentially, but we're not going to be using it. And in this tutorial, you know how the communication with the server would work. But essentially, so since everything, I know you actually haven't run the cell, so you should do it. So the first cell, what it does essentially downloads and compiles Allegro. Right. Okay, thank you. I was like, I don't see the comment. Okay. Okay, so the first cell just runs the test model. So you see that in the configs folder of NeQuip and Allegro, there are a bunch of tutorials, a bunch of YAML file, which is the style of file that we use to tell Allegro and NeQuip what to do. Minimal.yaml is the minimal input to Allegro. And this is going to take no time at all. So you can run this cell. I'm not even going to bother checking if the output is done because it's probably going to be done already. But what we can do is run the next cell, which is not doing anything. Ah, here it is. Maybe it wasn't done after all. So here you see a few interesting things. So like this is the end of the file that will come out of your terminal, or you're piping it to somewhere else like we're doing now. But this is kind of what you see. So depending on the loss function that you set up, which you will be looking at it a little later, but depending on the loss function you set up, there are different columns in this file. Here we're just training on forces. So you get the force MAE and the force RMSE. You see that the epochs, the training stopped at, so the kind of iterations of your learning process. Here it's capped at 10, so you reached 10. And you can see this because if you look at the output, it says stop training max epoch. So this is not a good way to do your training. You shouldn't stop your training based on max epochs. It's something that you should set up, so not to go to infinite number of epochs. But, you know, this is the minimal example after all. But what I want to see is the actual features, no, features is really the wrong word here. The actual parameters of Allegro and NeQuip that are important to look at when you train a model. So as I said, training is a little bit of a black magic. So these are the sort of things that I cannot give you any transferable recipe, but you should develop, if you're planning to use these models, a sense of what they do and how they matter in your simulations. So going from the top, Lmax is essentially the cap that you put to your spherical harmonics. So if you increase Lmax, you increase the angular resolution of your model. It's very, very related to the final model. Yes? Or the tensor product. Yeah. But, yeah. Oh, yeah, one thing I didn't say. Please ask questions. Yeah. No, it's a tensor product, yeah. No, because you can, well, the spectrum wants you to do the tensor product, so you cap that. Yeah, so please ask questions if you have questions. We're here to learn, so. The num layers is the number of layers in your model. Higher is better, as you can imagine, but it's also more expensive. The number of tensor features is essentially the size of your tensor vector on the vector, the size of the vector of the feature vector size. Oh my god, I cannot speak right now. Here, 32 is actually pretty high. 8 works. Does it give you the best results? No, but sometimes that is enough. Number of Bessel function bases. That's an obscure parameter, but it's actually pretty important. So one parameter that's not here is actually the cutoff radius. So we discussed these models have a cutoff radius. If it is the message passing in Equip, that is the radius that gets multiplied every layers. If it's Allegro, that's the hard cutoff. So it doesn't see anything past that. But the issue is that if you modify the radius, which you should, you might end up with a too low density for Bessel function. So you cannot describe your radial dimension appropriately enough. So if you're in a position of decreasing the maximum radius, you're probably fine with the default value, which is, I think, is that one, 8. If you're increasing the hard cutoff radius, you might want to increase the density of your basis function so that you can actually have enough resolution in the radial dimension. So in a sense, number of Bessel bases is the equivalent of Lmax, but in the radial direction. Max number of epochs, well, that's the least important one we already discussed. Here I provided kind of an ugly looking script to essentially change some of the parameters from the minimal YAML file. So these are all essentially the parameters we just described. I actually, there's also the batch size. Batch size, okay, batch size is basically how many data points you're looking at the same time. So if you do 1, it's normally more precise. If you do higher, it's smoothen your training. But sometimes that is at the cost of accuracy. But in return, you might end up, for those of you that have done machine learning training, sometimes you see that in the loss function or in the error function, whatever, you see spikes in your training. You can get rid of those spikes by increasing the batch size. The spikes can be really bad because once you have a spike in your loss function, you might not be able to go back to your original training kind of curve. So I found that increasing batch sizes does help. And of course also makes your training faster because you're kind of parallelizing the job here. So here with the updated YAML file, we're changing Lmax. The max number of epochs, we're doubling it. And everything else is kind of staying more or less the same. I think I increased also the number of layers. But so if you run this cell, and please run them all because at the end there is a plotting function that uses the output files. So if you don't do it, I don't know what's happening. So here we generated a new config file, which I call minimal boosted. And then we do the actual training. Okay, this might take a little longer. Oh no, this is the one, sorry. But we can actually tail the file and see what's happening. And I kind of like to do this because it gives you a sense of what's happening. As I said, I'm kind of wary of the spikes in forces, accuracy and stuff like that. And here, where did it go? Here. You see that it still reached the really important because essentially, if you think, I kind of alluded this during my talk, but for every snapshot, you have a lot of forces, but 1 energy. So you need to be careful with the weighting between the two. If you do add the flag per atom loss, the model itself takes care of the imbalance between the two. And that's why 1-1, which is the relative weight of forces and energy, is set to 1-1 and not 100 or something like that. The next line, I also would argue, is really important. So starting with a decently high learning rate makes you jump around a lot. But eventually, that's not what you want to do. So once you identify a good kind of set in your learning function, you want to start decreasing that learning rate in order to converge. So this tells the scheduler, essentially, if the loss function doesn't change by this much for this many epochs, half it. And it keeps doing this up to a certain threshold that we can set. And that's done in the next 3 lines. So the first of the next 3 lines is a wall time stop. So, it's quite useful for clusters. The second is the one I was talking about. So that's the lower bound for the learning rate. 1 to the power of -5 or -6 are normally good numbers. Is essentially, again, the convergence of the learning rate since you're halving it, if the loss function doesn't change. And, this is related to the patience over the loss function. I would say it's not as important. In this case, let's increase the max epochs to 100, and hopefully we reach a state where the model that we train is not stopped by maximum number of epochs, but some of the other flags that we actually set up. So now we created another model, another YAML file, which is the minimal boosted smarter, that we can run. Now let's deal what's happening. This is going to take a little longer because the maximum number of epochs is now set to 100. Here it goes. You still see that it's pretty fast. This is a small training data set, so it's like 1 second per epoch. You're never going to see this in real life, so appreciate it while you can. You can already appreciate probably that the error is going down pretty fast, and we're already below what we got earlier. But I would like to focus more on the learning rate. So right now it's still 0.002, which is the learning rate that we set it at the beginning. But soon you'll see that once the loss function plateaus a little bit, that is going to be halved. And if there you go. Now we are like a 1. If I size this correctly, I think an epochs 98, it should stop. In the meantime, does anyone have questions so far? Yes. Say again, sorry. Yes. That's an hyperparameter. So it depends. You need to be really careful because, for instance, I'm doing a project right now where I have 70,000 DFT calls in my training set. So my epoch takes, one epoch takes, I don't know, 3 hours. If you set the default value, which I think is 50 epochs at roughly constant loss, that wouldn't work very well, right? You essentially are stuck in the same spot, full stop. So in that case, I lower it to like 3 or 4. So it depends a little bit on your system that you're interested in, the size of the training set, but it's definitely a parameter that you should change. In this example, which actually didn't work like I wanted it to work, but in this example, let me check 1 second. I think it's this, schedule patience, set to 3. I think the default might be 50, but it depends on your training set size. The rule of thumb is if your epoch is long, lower it. Yeah, so Nequip and Allegro are unitless, so it's in the units of your training set. So if your training set is in EV per atom, the force is going to be in EV per atoms. If it's milli-V per atoms, it's going to be milli-V per atoms. I think milli-V per atoms, I want to say, but I'm not 100% sure, to be honest. Yeah, I think it's milli. Given the number, I think it's in milli-V per atoms. Yep. Yeah. Okay. I changed the loss function. I included energy in the loss function, and I told the network to weight forces and energies appropriately in order not to outflow the network with forces rather than energies. I told the scheduler to lower the learning rate appropriately, what we were discussing just earlier. I gave a maximum wall time. I gave a minimum learning rate, since we're changing over time, and I gave a validation loss criteria. Yeah, in any realistic scenario, you're gonna, put the number of epochs, really high. That's not normally how you should stop your training, and normally you should let the the learning rate to spiral down to your minimum rate. That's what I do in my trainings. Any other question? Okay. So we still reached max epochs. This was not happening when I was doing these validations, but oh well. Let's plot. So this is another plot that if you do this sort of things, you are going to do many times. Let's plot the validation of our trainings. Hopefully there's... there you go. So this is a normal learning curve. And you can also see the spikes that I was talking about. So the first, actually all of them are stopped by epochs, but you can quite clearly see that the first two were completely not done. And you can see in the third one, the action of the adaptive learning rate halving. And that's what allows you to essentially converge smoothly to your loss function. The spikes I was talking about are these ones. They're actually fairly small in this case. You can very clearly imagine ways this would not be the case. So for instance, if the batch number 1 was looking at the solid part of your system because of how the data was picked, and the next batch, if it's set to 1, it's exclusively looking at the liquid part of your system, there's going to be essentially no correlation between your adjusted weights between the two batches, and your loss function is going to jump. How much it jumps is how much uncertain it is compared to the previous step. And as I said, there's something to be wary, because if it jumps too much, like here you can see that the jumps don't really affect the general trajectory. But if it jumps too much, you're going to end up in a situation, I don't know, do you see my mouse? Yes. You end up in a situation where if this jump was much higher, instead of going back to the original kind of loss curve and go down, it would jump and then it might converge at this level. It just never finds the original trajectory it was on. So be wary of this. The way you fix this is by increasing the batch number. Are there any questions? Yep. Yes. I don't know if I would call them independent, but yes, these models have a seed number. So maybe we can open the so here it is. You have two seed numbers, one for the data set and one for the model, and these are set to the most likely password of everyone's phone. If you change this, your learning will change. I would not use this as a proxy of, model uncertainty or something like this. Yeah. Yeah, down to machine precision. It's the same output. Yeah. Yeah. Yep. I honestly think it's fairly improbable, and just because in high-dimensional space, it's very, very difficult that you are in a negative curvature in all directions. So I would say that if your model is very, very small, very likely. If your model is big, there will always be a saddle in one direction. I think there are studies that say there is a new iteration of Allegro. Actually, I think this is that one. Never mind. Scratch what I said. So here we're using a constant cutoff for all the species. It doesn't have to be the case. So with the most modern version of Allegro, you have essentially a matrix of cutoffs where the diagonal would be, and if you're setting a lower cutoff for the hydrogen carbon, you're saying, well, I don't care as much about my hydrogen being accurate. As cases, because that has implications on the final inference speed at the production level. Yep. It's very hard to answer the question. Like, it depends a lot on the system, your training data, and such. I would say inference. Like, I can tell you in the system I'm looking at right now, I gain 40% speed up by neglecting some edges, essentially. It's significant. As I said, I feel like when you do, I would say science in general, but like this type of science in particular, I feel like it's important to make a list of things that you care about getting right. Because if you prioritize getting right everything, you're going to spend a ton of time and you will never achieve it. So set a criteria that you're happy with and stick to it. Yep. Horrible. Scaling in what sense? In speed, in accuracy, in... I would say between 1 and 2. Yeah. Like 1 and 2 has probably one of the biggest improvements. After that, you still get improvement, but it gets so expensive. The issue is also Lmax is what really drives the memory consumption of your GPU, which is a little technical, but essentially, A100. So this cluster is A100s, right? So they have the version of A100 with 40 gigabytes of RAM memory. Okay. If you increase max to 7, you're gonna blow up the memory consumption of your model, and you're not gonna even be able to load it on the GPU. No, it's related to the cap that we impose on the tensor product between the spherical harmonics. Also, Allegro doesn't have message passing. Yeah. Anything else? Don't be shy. I train a lot of models, so if you want some advice, I train too many models. Okay, let's move on. You can always ask questions later if you're interested. Okay. Now, I guess we pre-downloaded all the data set too. Is that the case? Okay. So now we graduate from, I don't know what I'm doing anymore. We graduate from essentially using the mock data that's provided with Equip and Allegro to actually doing any simulation. So it's still going to be a relatively easy simulation. We're going to do silicon, bulk silicon. So I uploaded on my Google Drive a training set for bulk silicon. I don't remember how many data there are, but maybe 150 snapshots. Sorry, let me ask you again. It's in the tutorial file, right? Because I don't see the download lines. Yes. Okay, perfect. Yeah. Okay, perfect. Yeah. Yeah, if you're using the Colab, there are going to be another 1 or 2 cells to automatically download it from a Google Drive. But so this silicon folder is what I was talking about. So the silicon YAML file is the training file we're going to use. I think it's fairly similar to the boosted smarter one that we just created, and the silicon trajectory is the data set itself that we're talking about. So we can run this. It should also be pretty fast. Tutorial. I don't remember where this stops, so there's another great occasion for questions. So say the question depends on the hyperparameter. So cutoff is the simplest one. So if you're looking for atoms to interact, there are, I don't know, catalysis. If you're hoping to the hydrogen to bind to the platinum and starting to feel the interaction when it's relatively far away, if your cutoff doesn't include that distance, it's going to be decorrelated until it randomly fluctuates next to that. So like our max, so the cutoff radius is the maybe most physically sound one. So the way I do it, for instance, I have a kind of a workflow that goes through the data set I created for the network and plots essentially radio distribution functions. And then, you know, I have a few picking criteria. Is it the first minima? Is it the second minima? I want a hyper model. I want a model just to get by. So our max is definitely the most analytical one. L, number of layers, feature vector size. All of those, my go-to is really the minimum I can get away with, because all of those have implication at the inference speed. What else? Yeah, I think those are the major ones. Do you have anyone in particular? Yeah. Unfortunately, it's not a very satisfactory answer, but as I said, it's black magic. Yep. Okay. I don't know. I think it might be 6 because it's in the tutorial default. So 6 is actually relatively long for these models. Quite often it can be 5, 4.5. So if you think, so this is bulk silica. So we're actually plotting the radio distribution function after the simulation, so we can look at it. I think 6 encompasses both the first and the second peak. So you're feeling not the next label. That's normally what I do, yeah. Okay, the training is done. I think it was also stopped by maximum number of epochs. So to go back to your question about units, so you can see here that I'm using EV pair. So now the number is in the a few zeros down. So there's the good and the bad. Like it's up to you really to keep track of it. And Equip is agnostic about it. Max number of epochs, blah blah blah. Okay, so now we go to the next ground stages of building a potential, which is the deploying. It's a relatively fast and painless operation, and also there is no input from you except writing the line of code. But again, more meaningfully, what this does is it compiles network into a static version of it that then you can use in LAMPS, for instance. So we do this. It's as I said, very, very painless now. Okay, I don't know what happened, but we do have a Lloyd model. So let's try to ignore this this stuff. Okay, now are you guys familiar with LAMPS? Yes, no? Okay. LAMPS is a massively parallelized molecular dynamics code, and in my opinion, one of the best out there. So now we're essentially writing an input script for LAMPS. So when you do that, I guess the 3 lines that make it different compared to lamps run are the lines relative to Nequip or Allegro, and are essentially this two. So we also wrote, of course, hairstyle, and that's kind of the jargon of lamps to say how atoms interact with each other for Allegro and one for Nequip, of course. So you need to give the pairs you want to use to lamps, and that's the first line here. The second line is telling which model to use. So the two objects are just all the interactions of this model should be taken from that file, and the elements that are in the file are silicon. So if you have silica, you will say an oxygen here, for instance. Then everything else, I think, is relatively standard lamps stuff. So I don't think it's worth to go through now unless you have specific questions. But maybe what we're doing here, as I mentioned, we are computing the radial distribution function of bulk silica, and then we're going to be plotting it. So this cell generates the input file for lamps, and this cell runs lamps, hopefully. Yay, it does. So look at the temperature, really messed up. That's normal though. So you are just injecting a bunch of energy in the system, and it's a very small system, so it's just fluctuating a lot. But it will converge to, this thing keeps going down, but see, now it's like a kind of fluctuating in a more thermostat friendly way around 300. Let's check in the input file for how many steps we asked. 5,000. Okay, we are at 1,000. So another great space for questions. Yes. Ooh. I have to double check the innings of Allegro. I want to say that they're always going to be metal, but I'm not 100% sure. I think they're converters. I need to double check that. Something I don't really think about because I always use Quantum Espresso and it's fairly consistent. I honestly don't remember. But the safest way is manually checking, right? So like whatever DFT engine you're using, outputs in whatever way, and then check which lamps units match it. But yeah, I mean, both Nequip and Allegro are fully embedded in the ASE, code essentially. So you can convert anything you want and reparse it and give it. Yeah. Yes. It's bulk silica. I don't know what we can see through this class. Are you talking about, sorry, a data file format or it's bulk silicon. Bulk silicon, yeah. Nothing fancy. So this is how it looks like. It's 64 atoms, whatever cell, and then you have the, vector positions of the atoms and the forces and the energy. Yeah. Okay, lamps completed in 2.5 minutes. We can be about that. Okay. So the blue line is the one that you just computed. It's the radial distribution function of bulk silicon with a machine learning potential. So congratulations for those of you that never trained one. You just did and deployed it successfully. The orange line is my attempt at scraping an experimental paper for the radial distribution function of bulk silicon. So you see that it's the smoothest curve of the two. But focusing on the more important things, like you did it. Of course, the rescaling in one, it's meaningless, right? Well, it's not meaningless, I guess, but not same temperature and whatever. That's not what you should be focusing on. What you should be focusing on is really the positions of peaks. So you're essentially reproducing perfectly the first two peaks of the distribution function of bulk silicon. And going back to your question, they are both well within the cutoff that we set. If this curve, that's actually what I use to set the cutoff, as I was telling to Kevin. So you can plot a first versus from the training data, and that's what I use to inform myself for the cutoff to peak. Because, yeah. Yes. So my personal philosophy is that I don't believe in extrapolation. No, for this type of models, of course. So as I was saying earlier, I normally don't make models to answer the questions of the universe. I make models for answering a specific questions. Like I want to know the reaction rate for a catalytic reaction. I want to know the crystallinity rearrangement as a function of oxidation for a few catalysts, or something like that. So I kind of map the physical phenomena that happen, and I make sure that I sample them in a training set. That's my way of making sure that essentially never extrapolate. I think extrapolation is very dangerous because I don't know of a meaningful way to, and I don't know if anyone knows of a meaningful way to have uncertainties of these models that are correlated not with the model itself, but with the ground truth, right? So you can do stuff like add a Gaussian layer at the end of this network and make it predict a value with an uncertainty associated to it. You can make it have an ensemble of networks and take the standard deviation of the ensemble. Those are not true errors. All of those are errors with respect to the model itself. In principle, nothing to do with the true error correlation. And in fact, if you plot those two, then it's pretty ugly. So I guess you can play on the safe side and say errors are below a certain, you try to eliminate the false positives essentially to begin with. But I don't know if, it's a not very satisfactory answer, but any other question? Uh-huh. You do? Okay. Past the cutoff? Is it past the cutoff? Oh, okay. Okay. Mm-hmm. I will go back to the experimental paper and see what exactly they were doing. Because, yeah, I think that would be the first source of error. So aside from that, try to probe the system a little bit better at the training level, the training data level. If the peak persists, it might actually, because structural data should be reproduced fairly easily. So I would be very worried. Okay. Well, if there are no other questions, this is the end of the tutorial. Congratulations, you trained your first potential. If you have questions, I'm around all week, and I'm happy to talk. So good luck, and just ask.